Hello, hello. I hope you're having a good day thus far. Let's look at exercises 1 and 2, the warm ups for section 3.2. We're going to review some stuff about elementary matrices here, which we did in section 2.4 way back when, back in the day. So you might need to recall some of that stuff because it's going to be useful for what we do here. And you're also going to be looking at theorem 2.16 from there. So yeah, give these a shot if you haven't yet, because the answers will appear in 3, 2, 1. And here are those answers. And of course, these are my own examples. So hopefully you came up with your own examples. For scaling a column, the determinant should just come out to be whatever your scalar was, because this should still be a triangular matrix, both upper and lower triangular. And because we have a theorem from section 3.1, theorem 3.4, that the determinant of a triangular matrix is the product of the entries on the main diagonal. And so that should just be 1 times 1 times whatever your scalar is. Likewise, the result of doing any kind of column multi-displacement operation, it should still be triangular with zeros on one side or the other, so its determinant should still be 1. This also, of course, agrees with the definition of a determinant. This is one of the main things that it should have, is preservation under column multi-displacement. So it should be unchanged. And with C, your determinant should become -1 because of the anti-symmetry theorem right here. Okay, for exercise 2, part A, yes, when you multiply the matrix A times the matrix E, each of these columns in the result is a linear combination of the columns of A using corresponding entries in the corresponding column of E as weights. So you're basically just doing the linear combination of the columns of A that this is describing, and the operation, that the column operation that transforms the identity to E is swapping columns 1 and 2, and we get the same result done to A to get AE, which is what theorem 2.16 says. Now, when I found these three determinants, the determinant of A is 6, the determinant of AE, well, to go back to a nice triangular matrix, we need to swap two columns, and swapping two columns using the anti-symmetry theorem is the opposite of -6. The same thing is true with the determinant of E. You still need to swap two columns of E to get back to the identity, and the anti-symmetry theorem says that determinant is -1. So what I notice is the determinant of AE is equal to the determinant of E times the determinant of A. Maybe you noticed something different. That's fine too. All right, so we will see in the next video some cool properties of determinants, which are maybe really surprising, but we can explain why they work by way of elementary matrices and the way they do column operations. So I will see you then.